So we're going to be talking about solving exponential equations in cases where you might want to use a logarithm. Now, technically you can solve any sort of exponential equation using this method, but generally this is reserved for equations where the problem might be difficult to solve without doing it this way. So previously you may have learned about how to get common bases and solve using that method. This is if that method doesn't work for you. So a little bit of background on it is, first of all, a reminder of what a logarithm and an exponential are in terms of each other. So when I have a exponential, we have our base, our exponent, and our answer. Now a logarithm is another way of rewriting the exact same thing. So log of our base to get our answer is our exponent. So these two things are considered to be inverses of each other, just like adding and subtracting are inverses of each other, or multiplying and dividing. So we can play off of this relationship between exponentials and logarithms as a way to solve a problem. So instead of having to find a common base, you can use this method. And what it is just like when we would, for example, if I had x plus 2 equals 7, I would subtract the 2 from both sides in order to use an inverse operation to move that 2 and finish solving for x. We can do the same thing here. So I can say I'm going to use a log of the same base that I currently have. So my base right now is 3, so I'm going to take the log base 3 of this side. Now just like we would in any other type of solving process, if I do something on one side of an algebraic problem, I have to do it on the other. And just like with any other process, inverse operations cancel each other out, meaning the log base 3 and the 3 cancel. And what we're left with is just our exponent answer on this side. And on the other side, it looks challenging at first. Log base 3 of 9. Maybe you know what that number is, maybe you don't. But I can actually use a calculator to get that number. So a little sidebar for us here is something called the change of base rule. So whenever you have a base that's not a 3, and your calculator may or may not be able to handle that, mine is not, the way to get an actual number here, a decimal answer, or an integer if we're lucky, is you take log of the large number, so in this case 9, divided by log of your base. Since most calculators are set up in base 10 and they can't handle having a base of something other than 10, in this case 3, the change of base rule gets us to a place where we can get the answer that we would have gotten if we were able to type this in as normal in our calculator. So log of 9 divided by log of 3 gives me an answer of 2. And then I could finish solving this problem if there was any more to do. Otherwise, that's just my answer. So we're going to try that again with a little bit more challenging of a problem. So it says e to the 2n power equals 10. Now you may remember that e is a special type of base. It's the base that goes with a natural log, meaning that the inverse operation here would be the natural log, or ln. Now if I do that on both sides, just like we did with the log base 3 over here, the ln and the e cancel out. I'm left with 2n equals, then in my calculator I can type in the natural log of 10 and get an answer. There should be a special button on your calculator that says just ln, in case you didn't already know that. And I get 2.3026. I'll round to 4 decimal places. Now this is a linear problem that we know how to solve. I can just divide by 2, and I get an answer of 1.151. So this process is slightly different than what you've learned, just because it gives us a way to deal with problems where we don't necessarily get nice numbers. So your old method of finding a common base works for this type of problem, where we get an answer that's an integer. That's fine. But when we have a problem that's a little bit more challenging and a little bit more difficult for us to figure out, it's nice to have this other method that allows us to kind of sidestep dealing with an exponent variable. So I've made up a couple challenging versions of this that we can work through. Now, I want to remind you that we're following our order of operations. Meaning, I need to get the piece that is an exponent by itself first before I can use this rule, meaning the 11 to the k plus 5 needs to be by itself on one side of our equation in order to solve, which means we have to get rid of anything that's outside of that, in this case the minus 8. So using our order of operations and how we solve things, we would add that 8 to the other side. Now we're set up just like we were before, where we had a base with an exponent equals an answer. So we're ready to start solving them. So how we do that is we use a log with the common base that we have. So our base is 11 because that's what's right here. And we do that on both sides. On this side, the log base 11 and the 11 cancel. They undo each other. Over here, this is actually an integer. So in my calculator, I'm going to type in log of 31 divided by log of 11, and I'm going to get a number. Make sure you close all your parentheses when you're typing that in. And I end up with 1.4321. Now I'm ready to continue on with my solving process. So I can go back to the beginning of our order of operations and undo adding 5 by subtracting and get a final answer of k is negative 3.568. Now if you're ever unsure or you feel like that number might not be correct, you can type it into the equation exactly where it would go. So in my calculator, I'm going to type in 11 to the negative 3.568 plus 5 minus 8. And when I type that in, what I should get out is about 23 or 22.99 or something like that, where our rounding error is the problem. So 11 to the negative 3 point whatever plus 5, and then minus 8. And I get really close to 23. I get 22.99. So if you're ever unsure, just type it in where it belongs, and that should check it out for you to make sure that you get an answer that makes sense. Let's try another problem like that. So, following order of operations, I need to get the exponential piece by itself. So right now I am multiplying by negative 9. So I need to undo that by dividing by negative 9 on both sides. So I end up with 8 to the 7n power equals 9.1 repeating. We're going to get rid of our exponential by using a log of the same base, so this 8 on both sides, so that these can cancel, and I'm left with 7n. On the other side, I'm going to take my log of 9.1 repeating divided by log of 8, and I get 1.0625. And to finish solving, I'll divide by the 7 here. And I end up with n is 0.152. You may have noticed that while I'm solving, I always tend to round one number further than I actually need. So here I rounded to 4 decimal places, and my final answer was in 3 decimal places. That's just to help avoid some of the rounding error that we might normally have. So I just go extra decimal places before I get to my final answer, just to make sure I'm a little bit more accurate in my final answer. So let's try another. First, I would subtract the 9 to the other side using my base to get rid of my exponent here. I end up with negative 2r equals, and then log of 90 divided by log of 19 in my calculator gives me 1.5282. And then I can divide. Now I mentioned earlier that this type of method will work for any type of problem, even if you would get an integer answer, because some students like to have a method that works all the time. Now this method might not be the most efficient when we're dealing with exponential equations that could use a common base, but it will get us there. So in this example, I know that I could find a common base between 4 and 64, but let's just say that that method's a little challenging for me. So I'm going to choose instead to use this logarithm method. So I've got my exponent piece by itself, which means that I'm ready to take the log of my base on both sides. By doing that, the log base 4 and the 4 cancel, and I'm left with 3x minus 1. This, just like before, I can type into my calculator. So log of 64 divided by log of 4, and I get 3. I can add the 1 to both sides and divide. So while it's not as efficient necessarily as the method of finding common bases, it does give us the same answer in the end. So if I were to do this using a common base method, I would have 4 to the 3x minus 1 equals 4 to the third. And then we said if you have common bases, you can get rid of them, and then you would solve. The reason that these two methods seem so similar is because this idea of getting common bases and then crossing them out is literally doing exactly what we're doing here. It's just having you get a little bit more familiar with how numbers relate to each other. So they're actually the same method, it's just a simpler way of looking at it. One more try of a little bit more challenging version of one that you could do either way. Now, like we said, you need to get your exponent piece by itself first, which means I need to divide by this negative, or this 1 over 625 on both sides. Once I do that, I have 5 to the negative 2p minus 3 equals 625 divided by 1 over 625 gives me 390,625. Use a log base 5 to get rid of our exponent. And I end up with negative 2p minus 3 equals, and then over here I get an 8, and now I can finish solving. So the entire method here, if we're breaking it down to steps, when you are given a problem, you need to get the piece that has the exponent by itself. There should be only one base and exponent pair in the whole problem, and it should be on one side. Use a logarithm to get rid of that base on both sides, and then solve like you would any other linear problem.